Hi viewers, welcome to my class on mechanics of materials. In this class, I will be explaining how to find out the change in length of a uniformly tapered bar of circular cross section. We already know how to find out the change in length of a bar of uniform cross section. When area of cross sections are same throughout the length, you can find out the change in length using the equation PL by AE. That is, P is a load, L is a length, and A is the uniform area of cross section, and E is a Young's modulus. So PL by AE equation can be used when the bar is of uniform cross section throughout its entire length. But in this case, the bar is of circular cross section and its diameter is varying from D1 to D2 at the other end. As shown in the figure, it is of circular cross section. This is only a front view of the tapered rod. So it is area of cross section is uniformly varying. Area is gradually increasing. In this case, it's increasing from left end D1. It is increasing, gradually increasing to D2 at the right end. So in this case, we cannot use the equation PL by AE because each portion, if you take, I have shown a differential length here at a distance x. Now this portion, if you take, this portion is also subjected to same tensile load because it's only axial pull. Every element, any element you take on this bar, it will be subjected to same axial tensile load. So this element, if you consider, which is of differential length dx, it is also subjected to same tensile load. Now elongation in this element, and if you consider an element somewhere on the right end, the elongation in that differential element will be different because this will have more resisting area. Area is more, area of cross section is more to resist that load. When you come to the right end, the area of cross section is more, whereas at the extreme left end, you have less area resisting this load. So more deformation will take place. When area is less, it will be weak in resisting the forces, and more deformation will take place at the left portion compared to the right portion. So deformation taking place in different elements is going to be different from left to right end. So we need to consider all such deformation in small differential lengths and sum up to get the total elongation. So for that we can consider differential length. Differential length means very small length. When you consider small length, you can consider the area of cross section, change in area of cross section, and in that differential length to be negligible, and you can use the equation PL by AE for that differential element because area of cross section, so this diameter and the diameter at the right end of that element, it can be considered to be same because it's a differential length, very small length. So the diameter change in the differential length can be neglected, and you can consider this small length dx, the variation of diameter can be neglected, or variation of area of cross section can be neglected, and that can be treated as a bar of uniform cross section, and you can find out the change in length in that small differential length. Then you can all deformations in all differential lengths you can find out and then sum up. So that is integrate, find out the elongation or change in length in a small differential length, and then integrate. Integrating means finding out the deformation in all such elements from left end to the right end. That means x varying from 0 to L. So you are considering an element at a distance x with a differential length and find out the deformation in that element, and then integrate. X can change from 0 to L to get the total elongation. That is the idea of finding out the deformation of a uniformly tapered bar. So in that case we need to find out the diameter here. When you are considering a section at a distance x, you should know the diameter here. As I told, this is uniformly varying cross section, so the diameter is gradually increasing. Suppose at the end of 1 centimeter, if the diameter increases 1 mm, at the end of 2 centimeter, the diameter increase will be 2 mm, and at the end of 3 centimeter, the diameter increase will be 3 mm. Every 1 centimeter, the diameter increases by 1 mm. So that is a uniform variation of diameter. Whereas at the end of 1 centimeter, if the diameter increase by 1 mm, at the end of 2 centimeter, the diameter increases by 2 mm, and at the end of 3 centimeter, the diameter goes to 5 mm. That is not a uniform variation. So uniform variation means every unit length, the increase should be same. So that can be considered as a uniformly tapered bar. That can be considered as uniform variation. Now to find out the diameter, so you can find out the change in diameter. Change in diameter, what is the change in diameter in the entire length of the bar? In the total length of the bar, the change in diameter is d2 minus d1. Increase in diameter in this case, d2 minus d1 will give the increase in diameter. Okay, so d2 is the diameter at the right end, d1 is the diameter at the left end. D2 minus d1 will give the increase in diameter in the length L. So this increase is taking place for a length L. So d2 minus d1 is the increase in a length L. So what will be the increase in 1 mm length? For a 1 mm length, it is going to be d2 minus d1 by L. So that is going to be the rate at which it is increasing, or the increase in 1 mm length. Okay, d2 minus d1 by L is increase in 1 mm length. So what will be the increase in x mm length? 1 mm length, it is d2 minus d1 by L. For x mm length, it is going to be d2 minus d1 by L into x. So this portion, d2 minus d1 by L is in 1 mm length, d2 minus d1 by L into x is in x mm length. So that is increase in diameter in x mm length. If you add the diameter at the left end, d1 plus increase in diameter at the end of x mm, that will give the diameter here. So d dash, the diameter at a distance x, d dash, I am taking d dash, diameter at a distance x from the left end is d1 plus whatever diameter is there at the left end, plus rate at which the diameter is changing with the distance, multiply by the distance. At what point you are taking that element, the distance x, that will give the diameter. So this three-dimensional view of the bar subjected to load P, and it is one element is taken, an element is taken at a distance x, and that element is separately shown here and is subjected to axial pull P, and the elongation on this particular element has to be considered. When you consider this element, you can take it as a uniform area of cross section. So the diameter change in that differential length can be neglected, and you can find out the elongation in this differential length using the equation PL by AE, but L is going to be dx because that is differential length dx. So length of the element is dx. Area you should calculate based on the diameter at that point, d dash. Okay, so Young's modulus is common for the entire material, and P is also common because it's subjected to axial pull P. Now if I replace this d2 minus d1 by L as k, you can write this as d1 plus kx. Instead of writing d2 minus d1 by L throughout the derivation, I'll just use a simple notation k, where k is going to be a constant d2 minus d1 by L. So d1 plus kx I can write. So I'll write it as d1 plus kx, where k is d2 minus d1 by L. Now area is going to be pi by 4 diameter. This is a diameter at that point. So pi by 4 into diameter square. So pi by 4 into d1 plus kx square. That is area. Whatever diameter is there, diameter is d dash, which is d1 plus kx. So pi by 4 into d1 plus kx square is the area at that point at a distance x from the left hand. Now you can find out the change in length in the differential length as delta L dash. I am just putting dash, that is only in the differential length whatever change is taking place. In this case it is increased because it is an axial pull. P into dx by a dash e, where a dash PL by AE equation only, but A is a dash, L is dx. So now I am substituting this area pi by 4 into d1 plus kx square into E. Length is dx. Now to find out that this is only in the change happening in differential length of the element. To find out the total change in length, you can integrate it from 0 to L. So 0 to L, this quantity you integrate from 0 to L. Now the constants you can take outside. P is the axial pull, which is constant for all the element. All the element is subjected to same pull only, P, and pi by 4 and E all constants. So if you take this outside, 4P by pi E will come outside, and then rest of the things will be inside the integral. So 4P by pi E into integral 0 to L dx by d1 plus kx square. So this is the required integral. Now 4P by pi E, now you need to integrate it. Integration I have separately shown here. Integration of dx by d1 plus kx square. You can write it as d1 plus kx raised to minus 2 dx. So this I have taken to the numerator and written. Now the integration is d1 plus kx raised to minus 2 plus 1 divided by minus 2 plus 1, and you have to divide by the coefficient of x, k, and limit is 0 to L. So d1 plus kx raised to minus 1, minus 2 plus 1 minus 1 divided by minus 2 plus 1 minus k, or minus 1 by k into k minus, this minus I have taken to the numerator. So minus 1 by d1 plus kx raised to minus 1, I brought it down. So k into d1 plus kx 0 to L. So this is written. So you can directly integrate and write it here. Minus 1 into k into d1 plus kx 0 to L. So minus sign is taken outside, minus 4p by pi e k, and even k is taken outside. So pi e k, 1 by d1 plus kx and 0 to L. Now let us apply the limits. When x is equal to L, you will get d1 plus kl, and when x is equal to 0, you will get 1 by d1. So when x is L, 1 by d1 plus kl, and x is 0, 1 by d1. So upper limit and lower limit is applied, you get this. Now cross multiplying d1 minus d1 plus kl divided by d1 into d1 plus kl. Okay, so that outside part is minus 4p by pi ek. Now so d1 minus d1, that will cancel, you get minus kl, and here I am substituting that for k, d1 into d1 plus k is d2 minus d1 by L. So that substitution is also made. D1 instead of d1 plus kl, k I substituted d2 minus d1 by L. So this k will get cancelled, minus of minus will become plus. Okay, and d1 plus this L cancels, d1 plus d2 minus d1 inside the bracket, d1 plus d2 minus d1. So minus d1 plus d1 cancels, you get d2. So d1 into d2. So in the denominator d1 into d2, k cancels, so you get minus L. Okay, numerator, this k I have cancelled, so minus L. So this L cancels, minus D plus D cancels, you get D2, D1, D2. So D1, D2. So this minus of minus will cancel, 4PL divided by pi E D1, D2. So you get a simplified relation. Delta L is 4PL divided by pi E D1, D2. So this is the deformation of a uniformly varying bar of circular cross section when it is subjected to an axial load P. So axial load can be compressive or tensile. If it's compressive, you can put P as negative, you will get delta L negative. If it's tensile, you put P as positive, then you get a positive. That positive deformation means elongation. Now, if suppose the bar is of uniform cross section, you can substitute D1 is equal to D2. D1 is equal to D2 is equal to D. Okay, if you put D1 is equal to D2 is equal to D, you get D square. Okay, pi D square will get, and if you take 4 down, pi D square by 4. Okay, if it's of uniform cross section, the diameter is not changing, diameter is constant, we can take it as D. So D1 is also D, D2 is also D. The diameters of left and right end are same. So D square will get pi D square, and 4 if bring it down, pi by 4 D square. Pi by 4 D square is A. Pi by 4 D square is area of cross section. So what you are getting in the denominator is AE, and 4 I have brought it down, so PL by AE. So even for a uniform cross section bar, this equation can be used, but there you will have D1 and D2 same, and you can substitute. You can go for a simple relation PL by AE, where A is pi by 4 D square. So it is a general equation which is even applicable for a bar of uniform circular cross section. So that's all for today. Thank you for watching.